our graphs well defined. We have our features, annotations of, it could be of nodes or edges. We can have annotated edges too with different features. We can do learning, okay? So we can learn on these graphs, and there are different things we can learn, all right? So here, this diagram summarizes the different types of learning we have on a graph. So we can do what we call a node level learning task or prediction. We can do an edge level prediction, and we can also do graph level prediction. So for example, for the node level prediction, we have a node, and what we want to do is we want to predict. So let me write here. So we want to predict the label of the node. So if it's a classification problem, so we predict the label. So which means we're doing classification. Okay. If we're predicting a score, then this is a regression problem. So we're trying to predict the value of this particular node, given the other nodes, and these all the other nodes would be, for example, these are the training nodes, and this is a test node that we want to predict its a value. Okay, so test node. So this is what we call node level prediction. We can also do what we can also do an edge level prediction, which means, for example, I have all these edges connecting my data, but I want to know or discover if there is an edge here. How can I know that if these two nodes are connected or not? So this is what we call a link or edge prediction problem, and it's one of the very challenging, I would say, problems to solve in deep graph learning. Okay, so prediction. So now the last one is kind of simple. So you have a whole graph, and you want to do a graph-based prediction. So you want to classify the graph. So this graph, you want to assign it a label. So this is, a classification problem. You want to classify it, or you want to give it a score. So you want to regress it, or you want to, for example, generate another graph from it. So generate another graph. So this is generative learning, another graph from it, okay? So you map this graph onto another graph or another output. So the output could be anything, okay? So it depends on how we define our problem, but this is the idea of, learning on graphs. So we can divide it into 3 categories: node-based, edge-based, and graph-based. Now let's look at 3 simple examples here. And if you guys are familiar with machine learning, this should be very easy to understand. So the first example is a graph classification example. So here we have an input graph A. So our graph has 6 nodes, and these are annotated nodes with input features that are stored at each node. So we apply what we call a graph neural network, and we'll learn this in the coming lectures, so just be patient. And after applying this neural network, we will get we'll learn new features. So we'll update these values right here. So you guys can see that in this example, the graph structure remains unchanged. So we have the same graph structure, the same structure. So the same structure, it means the A is actually fixed. Okay, so we have a fixed A, it's not moving. The topology here is the same, so we have the same connectivity. So what is changing is these guys, the embedding. So we are taking the input features, okay, and we are learning learned new representation, also called embedding. Okay, so we will study this in detail, but for now, just keep in mind that somehow through this graph neural network, I'm transforming this, this embedding, I'm mapping it into a new representation, and that's through the network or the mapping function that we're learning. Let's call it W, for example, okay? So now once you get, so remember, we're trying to classify a whole graph. So, if you want to classify a graph, so let's see. So we're classify a graph. So for example, the graph could be a molecule, and you want a molecule, and then you want to know if the molecule is poisonous or not, okay, to humans, okay, for example. So you're classifying a whole graph. It could be a brain network. So you want to know if this brain network is healthy or disordered, okay? So these are different things you can do, different classifications that you can do at the graph level, at the whole graph level. And to assign a value to that, so what you do after we get these embeddings that we learned, and we hope that these will tell us more about these nodes, right, in my graph, then we can combine them, stack them all together. So we just stack them here horizontally. And then what we do, we combine them, we integrate them, and then we can classify them. So we can use this vector to predict, you know, the classes of the class of this, you know, graph. Okay, so if you have 3 classes, it will give us some probabilities, like for example, 0.8 for this one and 0.1, 0.1 for the 2 other classes, which means this graph belongs to class 1. Now let's look at this mathematically. So what do we have here? So basically this is expressed as a, you know, like a linear, I would say, classification problem. So what we have with some, of course, we can have some, you know, hidden non-linearity somewhere. So linear is just for the sake of simplicity, but we can make it non-linear. So we'll also discover that in the future. But for now, for the sake of simplicity, let's say this is, you know, the predicted class probability. And it is calculated through the sigmoid function. So we have a sigmoid that takes in a learned bias. So this is a learned bias. Also a learned mapping vector or parameter for at the last layer. Okay, so this is here at the last layer. The learned embedding, so the final learned embedding. And this is a one vector. So basically, if we look at this, let's look at this value. What is this value here? So before we look at the purple value and we debunk this part, which is basically this whole equation, before we map it using linear algebra, let's define the sigmoid, okay? So the sigmoid function is an activation function that is used to predict probabilities. And we use it in classification. We use it also in deep learning in general. And the sigmoid looks like this. So if x is smaller than 0, is lower than 0, so it's negative, so we set it to 0 here. It gives you a value close to 0. But if it's like higher or larger than 0, then it's set to 1. Okay, so it's like it kind of approximates the step function, and I talked about this before. Why we're using the sigmoid has some nice properties, and it's a smooth approximation. It's a smooth approximation of a step function, okay? And it is used to kind of, you know, condense or map all values into a 0 or a 1, which means, you know, a yes or a no, like, which gives us a probability to a class very high or very low, all right? So that's why we use the sigmoid, and it's highly used in classification tasks and also in logistic regression and other things, all right? And this is a derivative of the sigmoid, so you can see the derivative of sigma of x with respect to x, and this is how the function looks like. Okay, so it has some properties, but I'm not going to go into the details of this activation or logistic activation function, but I just want you to keep in mind that the sigmoid actually allows us to map any input value onto either some, you know, somewhere like onto 0 or 1 closed values. All right, cool. So now let's get back to our node, to our graph classification task. So here we have our, you know, like mapping function of the neural network. So the neural network basically takes in what we call the learned weights. So this is the learned, these are the learned weights here of the whole network at the last layer. So this is our W, okay? So, and WK, let's say it has D values, so it is 1 times D. D is actually the size of the embeddings, okay? So it needs to be of the dimension of H because we're going to multiply it by H. So H is actually this matrix. And HK is the matrix that stores all embeddings for each node. So this is the embedding learned for node 1, okay? This is the embedding for the last node, node 6. So it stores these values at the K. We call it K because K here is the, the final layer, all right? And what happens is that, so we can remove the K completely if you guys want. We can completely get rid of it, but let's keep it there. So it's not, I don't find it annoying, so it's fine. Now what we have, we multiply. So this matrix, what is the size of this matrix? So first we have 1 times D vector. We have D times, N, where N is the number of samples. And here, this vector actually, the one vector, we'll have like N times 1, okay? So this is all a bunch of ones. And N times 1 vector. So if you look at this, if we do the multiplication between these 3 elements, you can see that the D cancels out the N, and we're gonna get a 1 by 1 value, which is this value. Okay, so we're gonna get a scalar out of this. So first we do what we call, so let me explain what happens here. So basically we are mapping, we're linearly combining first all these embeddings. So this happens through this vector. This vector is very important because this vector of ones takes in all the each embedding, okay, and it combines it across nodes. So after this multiplication, we're gonna get basically a vector that is D by 1. Okay, so we're gonna get a D by 1 vector that integrates or sums. It's a linear combination. It's like an average pooling. Okay, so if you guys are familiar with deep learning, also this is called average pooling. Pooling or mean pooling. So mean pooling, it means that I take all these values and I sum them up and I create their average. So I sum an average, and the average is created because we are dividing by n. So this operation right here, this whole block right here, is a mean pooling block, which means I am integrating the embeddings across all nodes. So I'm taking all these guys, and for each value, I'm creating the average of the first embedding, the first element across all nodes. I put the value here, and then I'm gonna take the second embedding, okay, a value across all nodes, and I'm gonna put it here, okay? So once I get this value, so now comes the real magic, is that the mapping through the learned weight. So this is what the network learns. So this is what, the network learns, this mapping function W for classification. And here, by taking basically this vector and multiplying it. So if I take this vector, now that is normalized, of course, because this output of the whole block, so duplicate, and I multiply, I'm gonna put it right here, guys. So this is my integration vector where I integrated all the embeddings across all nodes. All right, I take this, and what is happening here, copy, and then I do paste. No, paste image. All right. So what happens here is when I do this multiplication, somehow I am projecting all this vector onto the W. So this is basically, I take each element here, each embedding that dimension, and I multiply it by my mapping function. So the W is a mapping function that allows me to map this vector onto a target value, which is the predicted purple score. Okay, so it's the probability that we are after, and this gives us, the first element, okay? So this is very actually simple. It's not difficult. And then we add a simple bias here. So beta is a bias. You can also get rid of it if you want, or integrate it with W here. But we have a bias that we add to that. And then once we get the final quantity, we pass it through. We have a value. We pass it through a sigmoid. So if we have a value of 2, if this whole quantity is equal to 2, then we're going to get the sigmoid of 2, and it gives us 1. So that gives us the probability of 0.8, which means we have a high value there, okay? So for Y. So yeah, so that's how it works step by step. And now I think we can easily generalize, not generalize, so we generalize actually to graph. We started with the graph classification of based learning, and we can easily look at the node based prediction or node level classification. So here, for example, what we want to do, so let me move these a little bit further for things. Oh, okay, so average pooling, let's put it over there. All right, so in this case, we want to classify a node. All right, so the goal is that we have, for example, a set of nodes, and we want to color the nodes. So we want to assign a color to a node. So for example, brown or blue, or orange here, or blue, okay? So the blue color, for example, can denote, so it tells you that this is a picture of dog, or this is a dog, right? And this is maybe a picture of a cat. So it's a classification problem, okay? We have 2 labels here. So to classify nodes, we do the same thing. We take the original graph. The structure A remains fixed. So A does not change, is fixed. You can see it here, okay? So, and also towards the end. So it's the same thing. We didn't change the A, all right? So A is fixed throughout the whole process. And then, yeah, so we pass it through our neural network. We get the embeddings, which is the most important thing. So we learn these embeddings, and then we classify node from node, the node from the node embedding. So we use this embedding to discover or to assign a label to this node, a color to this node, to say, well, this is class 0 or class 1. So it's the same thing. So here we have simply, we do this for every single node. So we have the HK of node N. So N is the node, okay? So this is for each node. We map the node through the weights, the learned weights WK. So we do a projection here. And through this projection onto W, we get our, we add a beta K, all right? So we get this first element over there. So let's call it output 1. So output for node N, all right, plus and K. So we have K and plus the beta K. And as we add the beta K here, right, so we're going to get the final scalar that we will pass through our, sigmoid function. And this will give us the label of node, predicted label of node N. Okay, so this is the predicted label of node N. So here you can see, so simple, actually. It's much simpler because you don't need to aggregate, you don't need to combine or do anything. You just through this one. So here we did a mean pooling or aggregation through this vector right there. But here we don't need that. We actually need to kind of, take each embedding, pass each embedding through the mapping function that we learned, the W, and then adding the bias and applying a sigmoid, and we get the predicted label immediately. Okay, so that's a probability of the for the classes that we may have. So now we move to the last example, and that's even simpler. So the last example is about edge or link prediction. So in link prediction, the question that we're asking is, do we have a link between 2 particular nodes? So if we look at nodes 1 and 2, we want to predict the edge presence using their adjacent embeddings. Okay, so we look at these, we look at these embeddings, the embeddings of the neighboring nodes. So the neighbors of 1 and 2 are 3, 4, and 5. These are the immediate neighbors if we look at only one hub right here, okay? And by looking at these embeddings, somehow we can derive the embeddings of these nodes. So we can learn these embeddings of our target nodes 1 and 2, and then we can use these two embeddings to calculate a cosine similarity, or a sort of we apply a particular function just to measure the similarity between these two embeddings. And if they are very similar, we can say, oh, look, we discovered that there is an edge and the weight of the edge is 0.9. So it's very close to 1 if it's normalized between 0 and 1, for example, okay? So there are so many things that we can use for link prediction, so many different operations. So here, for example, we use the dot product, okay? So we calculate simply the existing of links. So this is, the existing or the, so it's like the probability of link existence between nodes M and N, okay? So it's the same thing. We're using the sigmoid function because it maps onto 0 and 1, so it's beautiful. So it tells you if there is no link or there is a link, okay? So what we need to do is, like, once we learn, so the key thing is to learn the embeddings right here. So once we learn very good embeddings here, very good representations of these two nodes, we can simply take their, dot product. So we take HM transpose and HN and times HN, and we get the final value, which we pass through a sigmoid. So you guys can see this is actually HM transposed, and here we have the embedding of M. This is also the embedding of a node N, HN. And this is the operation that we do. So a simple multiplication, which is here a dot product of M and HN. And we're going to get the scalar here that will pass through a sigmoid function, sigma x, which will get us the value YMN, in around 0, 1, okay? So that's pretty much it. So you guys can see that all these problems, okay, or all these learning tasks, they share one key component. And that key component is these embeddings. How are we going to learn these embeddings, right? How to represent each node. Because, if you're going to classify a graph, you're going to use the H of all embeddings of all nodes, the embeddings of all nodes. If you're going to classify only a node, you will check the embedding of a particular node, only a node N. If you're going to do a link prediction, you need to check the embedding of 2 adjacent nodes, okay? So it's all about learning this embedding or this feature representation using these graph neural networks. And once we learn how to do that, any task you can see is easily solvable. You can use these simple mathematical projections and linear algebra and equations and some nonlinearities for probability prediction to just get what you want, all right? So we'll learn in the next lecture, we'll learn about how to basically calculate these node embeddings. And yeah, so that's it for today. So an overview of adjacency matrix properties. And we covered a few graph types, and not everything, but the most important categories, and a few fundamental learning tasks here. Thanks very much. Do you guys